We'll get started. So today the topic for discussion is differential dynamic programming. I'm not going to introduce the complete algorithm because it's going to take a lot of time. But I'll give you like the broad steps of what differential dynamic programming does. And hopefully that'll give you an idea and also a reference. So that gives you an idea of where to go and look for in case you wanted more details. One of the reasons I'm not covering the entire uh, algorithm is because the paper that I'm referring to uses a completely different notation than what we are using in the class. And more importantly, their derivatives are row vectors instead of column vectors. So every expression in their paper is completely different from what we have done in the class, as a result of which I'm not able to map what their expression would look like in case we wanted to rederive it for the notation and convention that we are using in our class. So this algorithm, I think the algorithm dates back to 1965. But the paper that I'm using is computational aspects of discrete time optimal control. And this paper is from 1984. So 1965 paper is for a scalar state and scalar action. So not very interesting, but it contains the original algorithm. And then this particular paper is not very theoretical, and it basically spells out what the algorithm is extremely clearly, and therefore it's actually very interesting to read this particular paper. It's by Sidney Yakovich and Brian Rutherford back in 1984. One of the reasons why I'm covering this algorithm is because it is a very important algorithm for all the humanoid robotic stuff. Okay, so a lot of algorithms that, if in case you went into robotic industry in the future and you're doing any sort of robotic manipulation, it's quite likely that you will be using some derivative algorithm of differential dynamic programming. And remember that this whole topic that we are talking about, it sits within this whole umbrella of cost/model approximation. So we have a complicated problem. I have a very long horizon. I'm going to truncate the horizon using either rollout algorithm or MPC, model predictive control. But if I have a complicated state transition function and a complicated cost function, then how do I solve the problem for the finite horizon problem? So that's what we are trying to solve in this particular case. The setting is, let's see. I'm going to use the same setting, xt plus 1 equals to ft of xt ut. So the paper that I'm referring to, I think f does depend on t. Yeah, okay. And then I want to minimize over u or pi j of pi ct plus 1 xt plus 1 summation t equals 0 to capital T ct xt ut. In the previous lecture, what we said was, somebody gave me a reference trajectory, a u bar and an x bar that I'm supposed to follow. And I'm going to do small perturbations around that particular reference trajectory, and I'm going to do the cost approximation and model approximation. And that leads us to LQR problem that is part of your assignment, so you're already solving it, or you might have already solved it by now. There were a bunch of terms that we kind of ignored. There were linear terms and stuff that we ignored in that particular approximation, and that's because we always want x to be as close to the reference trajectory as possible, and we were looking for a closed loop control around that reference trajectory so as to track that particular reference trajectory. The situation is not too different here. Somebody has given me an initial trajectory to follow, and my assumption is that my optimal trajectory, optimal action and optimal trajectory would be in the vicinity of that trajectory that somebody has given me. So imagine a robotic manipulator. It's supposed to pick up an item, maybe a package or something like that. And some initial trajectory was figured out by someone. And that's the reference trajectory, that's the initial trajectory. And I'm assuming that my optimal trajectory to pick up the box is going to be somewhat in the vicinity of the initial set of actions that I was given. So the philosophy between the previous algorithm and the current algorithm is slightly different. Okay, and that's why it has a different name of differential dynamic programming. And there are many derivative algorithms that came out of this particular method. So what is given to me? I'm given a initial u bar 0 and x0. So this is the initial guess of what the optimal action is, and this is the corresponding trajectory. So this x bar 0, well, let me write it. So u0 is u10, u00, u10, ut0. So this is the initial guess. And my corresponding x0 is x00, x10, xt plus 1, 0. And this is the corresponding trajectory. So x t plus 1, 0 equals to ft xt0 ut0. The constraint version for this particular algorithm was studied in, let me write it here. So constrained was studied in this particular paper. So in case you want to know how to extend this to the constraint case, you can refer to this particular paper. This is the author's last name, Ono, and the paper is from 1978. So it came before this particular paper that I'm talking about in this class. Okay, so somebody has given you an initial guess, and you've computed what the corresponding trajectory looks like by using the recursion. And you know that the initial guess is not too far from the optimal solution that you're looking for. And you are looking for a feedback solution. You are looking for the action, optimal action, as a function of the optimal state. As a function of the current state. So what would be your solution approach? How would you solve this problem? So go back to 1965. We want to go to Apollo. The hidden figures ladies have given me this particular set of actions that I'm supposed to take in order to follow this trajectory. It's near optimal. So I know that if I follow her recommendation, I'm going to take 4,700 tons of fuel is needed for me to get to the moon. Okay, and back. They had to come back also. Okay, they were astronauts in that mission. Okay, so they need to go to the moon and come back, and 4,700 tons of fuels are supposed to be used. I want to compute the optimal solution to this problem, and I have a complicated FT and I have a complicated cost function. So one approach that we talked about in the previous class was, let's just approximate the FT and CTs around this, whatever the reference trajectory is, and run an LQR in order to solve the problem. Get ut as a function of, well, get delta ut as a function of delta xt. That's what we did in the previous class. What would you do in this case? So here is the idea. I'm going to look at the cost at the terminal state. So let me call this LT of XTUT. This is so that's my cost at the terminal time step, capital T. This is the cost to go, sorry. This is not the cost, but this is the current cost plus the future cost. So this is the cost to go. So I'm going to approximate this cost to go. I'm going to do a quadratic approximation, okay, not a linear approximation, and not the approximation we studied in the previous class. I'm going to do a quadratic approximation of this particular loss function. So I'll compute L hat T as a function of delta xt delta ut equals to half delta xt delta ut something let me remind you again, my delta xt is xt minus xt0, delta ut is ut minus ut0. So the difference between the action and the reference state and the reference action. So there will be some matrix here which will be complicated, plus some matrix multiplied by delta xt delta ut plus some constant. So what I did was I took the second order Taylor series approximation of this function, this cost to go function, and this is a second order Taylor series approximation in both action as well as the state deviation. I'm not just doing only action, I'm doing state deviation as well. What would this matrix look like? Anybody remembers? It would be gradient of second derivative of xu of LT evaluated at xt0 and ut0. And this particular vector is going to be the first derivative of LT of xt0 ut0. What is this constant? The constant is going to be LT of xt0 ut0. Okay, any questions so far? So we love Taylor series in this class. All we want to do is do Taylor series approximation from day 1 of the class to today is day 30 of the class, or maybe 29. And so I've done the Taylor series again around xt0 ut0. So this is the first term, second term of the Taylor series approximation, third term of the Taylor series approximation, and I've ignored all the higher order approximation. Everything else I've ignored it. I have come up with a new cost function L hat. Now I'm going to compute delta ut star by argmin over all delta ut L hat t delta xt delta ut. Because remember, delta xt is something that's given to me. I'm sitting at xt. I can sense my current state. This is my reference state xt0 at the time 0 at the initial time, and then I can compute this delta xt, and then I can minimize this L hat t in order to get delta ut star. It turns out that this particular thing is going to be it can be written in the form of alpha t plus beta t times delta xt. Yeah. So there will be a constant term in delta ut star, and then there will be some matrix multiplied by delta xt. That's what we'll get if you try to solve this particular problem. Remember that you're solving something like this in the LQR setting as well. The only thing in LQR is that you assume that the off diagonal terms are 0, and you remove this particular approximation as well. Now here the off diagonal terms are there, and this term is also there. So that's where this alpha t comes from. And then of course there will be beta t, which is going to get multiplied to delta xt. So because we are doing a different approximation, we are getting a somewhat different optimal delta ut star. Okay, I want you to contrast this. Go back to your notes from the previous lecture, and you will notice that in the previous lecture we only had this particular term and we didn't have this alpha t term. Today we have alpha t term because I'm not ignoring these two matrices and I'm not ignoring this matrix, so therefore I have alpha t here. Any questions so far? Does this sound reasonable? Okay, I have a complicated cost function, I have a complicated ft. I don't want to solve this complicated problem at every point of time. It's going to create a lot of headache for me, especially on the microprocessor or microcontroller that is going on a space shuttle all the way to moon and back, and it doesn't have as much computational power back in 1965. So I'll do this approximation. I can compute this derivatives and all that stuff beforehand, and I can store it on the microcontroller. So all I have to do is just evaluate these matrices and compute this alpha t and beta t. The expressions for these are given in the paper, this particular paper that I'm referring to. But remember that they are using a different way of representing the gradient, and therefore what we have done in the class is quite different. I mean, the representation of gradient that we are using in this class is quite different from that paper. So don't just blindly use that paper in your implementation. Yeah.
So this is only optimizing at the terminal step.
This is only optimizing at the terminal step. Okay. And then I'm going to get L hat t of delta xt delta ut star. This will be a matrix of delta xt transpose some matrix. Let me call this pt plus 1 pt delta xt plus qt and plus constant. And you know, whenever I'm writing constant, I'm just going to ignore it, okay, because constants don't participate in optimization. First derivative of constants are 0, so if I'm accumulating constants, I'm just going to keep ignoring it because I don't care about it. Okay, constants don't matter. So I get something which is a quadratic function. So pt is a matrix, it's an Rn cross n matrix, and this is a vector in Rn. So I get a positive definite, well, there is an assumption on positive definiteness of this matrix. So we'll assume that this particular matrix is positive definite. So that way I can actually do the minimization here and I can compute the optimal action. And then I get a positive definite matrix here, and that's my value function. It's a value function. By the way, I'm not calling it a value function for a very specific reason. We are not doing dynamic programming here. We are approximating the loss function. We are minimizing the approximate loss function. We get something which you can think of it as an approximation to the value function, but not the true value function. Okay, so that's why I'm not calling it a value function. It's a some approximation to the value function, which is quadratic in the deviation of the state. Always remember this delta xt is xt minus xt0. So it's just the deviation from the reference trajectory that I'm computing. Now I can substitute this L hat t at time t minus 1, okay, and I can solve this problem. Where should I write it? Maybe I'll erase this side. Now at time t minus 1, I'm going to define my LT of LT minus 1 of xt minus 1 ut minus 1 equals to ct minus 1 xt minus 1 ut minus 1 plus L hat t delta xt delta ut star. I'm substituting this particular thing right here. Oh, I'm so sorry. This should be qt transpose delta xt. Can you please make a change here? This is qt transpose delta xt. So it can't be in Rn. I have to get a scalar value because it's a loss function. So it needs to get multiplied to delta xt. And I'll keep going through the same process again and again. Okay, all the way up to time 0. I'll go all the way to time 0 and I'll have L0 of x0 u0 equals to c0 of x0 u0 plus L hat 1 of delta x1 delta u1 star. Okay, and I'm again going to substitute this delta xt with the state transition function and so on. And what I get is a recursion. Okay. At the end of the recursion, what do I have? I have these alpha t's and beta t's computed at every point of time. Yes.
Should the variables here still be delta, like delta xt minus?
Yes. So this is the loss function is in the original state, and L hat is in the, it's the Taylor series approximation around the reference trajectory. Okay, so that's what I'm doing here as well. Good question. So after going through all of this step, so I define this LT, then I do the Taylor series approximation here, then I compute the delta ut star here, then I compute the L hat t here, and I keep going back all the way to time 0. What do I get? At every point of time, I get alpha t, beta t, pt, and this qt transpose, right? I get constants also, but as I said, I'm just going to ignore the constants. I don't care about the constants. They don't participate in the optimization. So now I'm going to do the following. I'm going to set epsilon equals to 1, define pi t 1 or maybe pi t 0 of xt equals to epsilon alpha t plus beta t xt minus xt0 plus u t0. So then this is the step. Step 1, then step 2. If j pi 0 minus j of u0 is less than epsilon theta 1 over 2, then set pi 1 equals to pi 0 and go to, let me call this step 2. I think this is step 2 1, step 2 2, and this is step 1. Go to step 1, else replace epsilon over 2 and go to step 2 1. And theta is some hyperparameter. So this theta 1 is picked. Theta 1 is picked. I don't know, from experience. Okay, so what I have showed you is the steps that you need to take in order to get the first set of feedback policies from the reference trajectory, and then you go back to step here and you keep going, you go back and do all this calculation all over again, and then update your pi t1 again, and then get pi t2, pi t3, and hopefully at some point of time you would converge. Okay, so this difference will not be too much. So from pi 0, so pi 1 to pi 0, pi 2 to pi 1, right? So you will keep updating this strategies, and then you will see whether it's close to 0 or far away from 0. And if it is close to 0, then you are at the optimal policy. This is the idea of differential dynamic programming, which is quite distinct from the LQR approach. And the reason why it's distinct from the LQR approach is I look at the cost to go, I do the second order Taylor series approximation, and then I keep computing policies by picking a hyperparameter epsilon. So initially I've set epsilon equals to 1. I keep running this iteration. If it is improving a lot, then I'm going to update the policy. If it's not improving, then I'm going to set epsilon to epsilon over 2 and redo this whole calculation all over again. Any question so far? Yes.
Why is it not getting the optimal policy at the first time, the first step?
Because you are doing the, so remember this particular Taylor series approximation is happening around xt0 and ut0, and this is not the optimal solution. This is near optimal, but not the optimal, right? If it was the optimal solution, right, and you just want a feedback policy around the optimal solution, you can use the LQR algorithm we used in the previous this thing, or alternatively you can use this algorithm and you can get a feedback policy around the optimal trajectory. Any other question? So people in humanoid robotics back in 1990s to 2000 era, they were trying to come up with better versions of differential dynamic programming in order to come up with the locomotion problem. So the locomotion problem is, my robot is sitting here. I ask the robot to go there, pick up some item and keep it somewhere else. So that's the locomotion. You have to carry out a task, carry out a mission. And I have the initial trajectory. I have come up with some initial set of actions and the initial phase space for that particular robot, how that robot's joints and configuration of the robot is going to look like. And but it's not optimal. It's not optimal because the robot is might be taking some dangerous actions and things like that, and therefore it's not quite optimal. And using this approach, differential dynamic programming and new versions of differential dynamic programming, people came up with a whole bunch of algorithms for coming up with feedback policy. Remember, you get a feedback policy around this guess, and you keep updating the guess, right? So at time pi bar 1, this will become xt1, this will become ut1, and then you will redo this entire problem with the xt1 ut1 trajectory, and then you will do it again and you will do it again, and then you will get a feedback policy. So this is another class of approximate dynamic programming algorithm. The nice thing, so in LQR, you couldn't run an LQR again. Once you get an LQR solution, you get a feedback policy, you have to use that policy. Here, you can iteratively keep updating it. So you have, let's say you finished all this computation in 50 milliseconds and you have another 50 milliseconds to come up with the next policy. You can run this algorithm all over again and get something which is closer to the optimal solution. Okay, so there are many benefits of differential dynamic programming over LQR thing, because you can run it iteratively and you can keep improving the policy at every run of the update. Yes.
Does this mean that it can also be applied to systems that are changing over time?
Okay. Very good question. Can this be applied to systems that are changing over time? So as we know, almost everything changes over time. The temperature in the morning was sub-zero. Temperature right now is above zero. So certainly the temperature of outside environment has changed. And so can I apply this algorithm even if the situation is changing? So it turns out that you can't apply this algorithm, but you can apply a version of this algorithm, which is something we developed at Center for Automotive Research. Okay, back in 2020 or 2022 is when the paper came out, but we did it in 2020, and we applied it to automotive hybrid vehicles. Because in hybrid vehicle, as you're going on highway, as you're driving on the city, as you're stopping at a traffic light, everything changes, right? So and then we applied it also to air conditioning system optimization in vehicle. Okay, battery electric vehicle. And there also the situation is changing depending on the trajectory that you are taking while you're driving on the road. But it's not this algorithm, it's more complicated than this algorithm, and that's why I'm not covering it in the class. Okay, it's yeah, but we have done that particular work. Any other question? Perfect. So this is an important algorithm for approximate dynamic programming. The next algorithm that I want to talk about is again written by my PhD student Jianzhong P on singularly perturbed optimization. So let me erase the board and we'll talk about singularly perturbed. So what's the setting in singularly perturbed optimization problem? So the history for this particular algorithm is also pretty old. People have developed singularly perturbed, like optimal control for singularly perturbed system theory back in, I think, 1960s or 70s. But they were all in continuous time. There was nothing in discrete time. Then some people in 2010s wrote some papers in discrete time, but they didn't have constraints. So what our contribution was, this is from 2023. Uh, so my student was sitting in this class, Jianzong, who wrote this paper. He was sitting in this class in 2020. So I'm looking forward to your papers in 2027, 2028. Okay. So he was in this class in 2020, and I was sitting in a candidacy exam back in 2019, and I saw this system model, which is xt plus 1 equals to xt plus epsilon xt yt ut yt plus 1 equals to, let me not make f time varying, let me make it time invariant. And I have a constraint gt of xt yt ut less than equal to 0 at all t, and I want to minimize summation of ct t equals 0 to t xt yt ut. I didn't have a terminal cost in this formulation, but it's not too difficult to add a terminal cost. So this is the constraint, state action constraint. So the history for this is, well, I'll let you guys write and then I'll tell you the history. Meanwhile, I'll erase the board. Okay, so I was sitting in a candidacy exam back in 2019, and the student was presenting. He had this system model, he had this constraint, he had this cost function, and he said, nobody has done it in the past, so I'm just going to come up with some algorithm and I'll try to see if it works or not. And that's when I realized that somebody needs to come up with a theory for how to solve singularly perturbed system with state action constraint. Okay. Because it was a hybrid vehicle, again, we have worked a lot on hybrid vehicles in the past. So there's always some sort of constraint that comes from the battery pack, that comes from the motor, that comes from the engine, and so on. And as a result of which, this sort of constraint almost always has to be met. Okay. Sometimes you can choose not to meet the constraints, but most of the time these constraints have to be met. To give you an example, suppose the constraint is on NOx emissions coming out of the vehicle. Now you can choose to ignore the NOx emissions at some point of time, like you're accelerating, you're entering a highway, you're accelerating very hard, and so the NOx emissions are not going to remain within bound. But then when you're cruising on the highway or when you're driving within the city with not too much of stop and go traffic, then you can have under limit NOx emission. Okay, so that's some kind of constraint which legally has to be met, but sometimes you can choose to ignore those constraints. So anyways, that's the setting. So I'll give you a very specific example. Say you are going on a highway. Xt is the velocity of the vehicle, yt is the RPM. So where do you see RPM? You see it on your dashboard. On your vehicle dashboard, you will see the RPM of the engine. And the velocity doesn't change in 100 milliseconds. If you're going at 40 miles an hour and you floor the accelerator, how many of you have floored the accelerator before? Okay, very good. There are some free-spirited drivers in this class. Okay, so if you're a free-spirited driver in the class and you floored the accelerator, within 100 milliseconds, your velocity might go from 40 miles per hour to 40.2 miles per hour. So this is 40 miles an hour. Epsilon is 0.2. Xt plus 1 is 40.2 miles per hour. So xt plus 1 doesn't change much from xt within one time step. The RPM has a completely different story. You floor the accelerator, the RPM is going to jump up quickly, very quickly. The RPM is going to jump up. So you were at 1500 RPM, you floored the accelerator, the RPM would instantly become 2500 within 50 milliseconds. Okay. So you have a state that changes extremely rapidly. You have a state that changes very slowly. Okay. Same thing happens in a battery pack. You are charging you are braking the vehicle. The battery is not going to get charged, like the SOC is not going to go from, let's say, 50% to 55%. It's going to go from 50% to 50.05%. Okay, so the battery state of charge dynamics is not going to change much, but what's happening with engine is going to change very rapidly depending on what you're doing to the vehicle. Okay, you might be accelerating, decelerating, or whatever. So the SOC doesn't change much, but whatever control action that you are applying to the vehicle, that changes some of the vehicle states pretty rapidly. And now you have a constraint and you have a cost function to optimize. So the question is, how do you do that? Okay, that was the question that we asked ourselves back in 2023 or 2022. Now imagine that my xt is R2 and my yt is R8. So I have a 10-dimensional state in this problem. 10-dimensional dp. 10 different derivatives that I have to take at every point of time. Life is very complicated. Okay? I don't want to do this 10-dimensional optimization. I love this 2-dimensional optimization problem because then my state is very small and I can do the derivatives and all that optimization very quickly. Okay, with a 2-dimensional state space. So what would we do? Here is what we did. So have you guys, did I talk about curves of dimensionality? No, I haven't talked about curves of dimensionality. Okay, so what is curves of dimensionality? It didn't appear so far, but here is the idea. You have a two-dimensional state, you're doing dynamic programming, you're discretizing the state, or you're doing some sort of approximate dynamic programming technique. It's going to take you, let's say, 100 milliseconds to solve the problem for capital T time step with two-dimensional state. If you have a 10-dimensional state, okay, you will take 2 hours to complete this capital T horizon optimization. So imagine as you increase the number of dimensions of the state space, the amount of time it's going to take is going to be exponential in the number of states, like the dimension of the state space. So generally speaking, informally speaking, curves of dimensionality approximately is that the time taken to solve dynamic programming is the order of exponential of the dimension of x. So whatever is the dimension of the state space. So in this case, it would be dimension of x plus dimension of y. Okay, so exponential in the total dimension. Exponential of 2 is a small number, exponential of 10 suddenly becomes a very large number. Okay, and now you are going to take a very large amount of time in order to solve this dynamic programming problem. And we don't have the luxury because we are in a real time system. I need to be able to compute all of this in milliseconds, not in hours. Okay, so what did we do? So one of the things that you would notice is that happens in many of these singularly perturbed systems. For a given x and for a given u, y converges to some steady state value. So I'm driving the vehicle at 65 miles an hour on the highway, and I'm accelerating at 1 miles per hour square or 2 miles per hour square, whatever that acceleration is. There is an RPM that gets reached extremely quickly. So I reach some equilibrium RPM, and you can actually observe that in your dashboard. So it's not like I'm making things up. You can actually see on your dashboard that you are at a specific speed. You press the accelerator or brake at a specific point. The yt is going to reach the steady state extremely quickly. So we define this map. You can call this as a steady state map. So assumption, there exists h from x cross u to y such that f2 of x hxu u is equal to h of xu, and for every t, for every x, the set u such that gt x. And you have to make the assumption about differentiability. So all of these functions that I'm talking about are infinitely differentiable. H is infinitely differentiable, f1, f2 are infinitely differentiable, so that we have something that's a very smooth map, not a problem. Okay, so this is the equilibrium RPM for a given velocity and for a given braking or accelerating action. So this is the equilibrium RPM. Okay, awesome. So once you have this h function, remember the goal is I want to solve a dp only in xt. I don't want to have yt in that dp expression. So the way to get the dp expression in xt is as follows. You define f1 of h of xu as f1 of x hxu u, ch of t xu as ct of x hxu u, and then I solve the following dp. Minimize over gamma from xt to ut, summation t equals Okay, so what did we do? We renamed these functions f1, ct, and gt, the constraint, the cost, the dynamics evaluated at h of xu. So wherever there was a y, I replaced it with h of xu, which is the equilibrium dynamics for the fast state. I created a dynamic programming only for the slow state. Okay, so this is a dynamic programming only for the slow state. For the fast state, I'm just tracking this particular y bar t. And how do I track it? I can use LQR for tracking it. Or I could use some other way to make sure that I'm able to track this y bar t as closely as possible. So typically speaking, people use LQR for tracking this particular variable at a faster time scale. Because remember, LQR is much easier to solve at a faster time scale. You can't solve this at a fast time scale, but you can solve this at a very fast time scale. So you might take 100 milliseconds to solve this problem. You might be able to solve this problem in a matter of a few, just 1 millisecond or maybe a few microseconds. Okay, because this is all tracking is just matrix multiplication. This one, on the other hand, requires you to enumerate the state, come up with a value function, come up with a policy at every point of time. So this one takes a lot more time. When you are driving, who is actually solving this problem? So in autonomous car, of course, there will be a GPU which will be solving this problem. But when you are driving, who's the one solving this problem? What is this problem doing? It's figuring out how to press the accelerator or brake in order to maintain a velocity. Okay, who's solving that problem? We are solving the problem. So this is the problem that's going on in our head. We are solving this problem at every point of time. This is what the engine is actually doing. So you press the accelerator, you see the RPM move. That's exactly what the engine is trying to do, which is track whatever command you have given, whatever velocity you want to give, whatever action you are pressing, right? So whatever my current velocity is 40 miles an hour, I'm pressing the accelerator hard. This is the RPM that the engine is supposed to track, and the engine is trying to track that particular RPM. So this is again an instance of model approximation. So we had this very big, complicated 10-dimensional state space, state action constraint, very complicated cost function problem. I converted it into a low-dimensional DP problem and a tracking problem. And the reason why we wrote the paper is we showed that this particular algorithm is near optimal. So you are within some sort of suboptimality bound of the optimal solution if you were to solve this full scale DP with which will take this much amount of time. Okay. So that completes our discussion on the model / cost approximation. So I have a very complicated DP problem. I don't want to solve this complicated DP problem. So I'm going to do a cost approximation and I'm going to do a model approximation. And I'm going to come up with some way to reduce the computational burden for solving that complicated problem. So we studied 3 algorithms for it. One was LQR, the linear quadratic regulator problem, which is part of your homework. Second one was differential dynamic programming. The third one is singularly perturbed system, optimization for singularly perturbed system. In the next class, we are going to talk about the fact that now at every point of time, I've solved all this stuff. I'm supposed to store the value function and I'm supposed to store the policy. Okay, and the problem is I can understand the value function and I can understand the cost, the policy, because I can write down min and max and all of that stuff. How will computer understand, and how will computer store that information so that it can go to the moon and come back, or it can go to the Mars and come back? Okay, so what we are going to talk about is function approximation theorems and things like neural network transformers and things like that that are actually used to store these value functions and policies in the computer's memory. So that's going to be the topic for Wednesday, Friday, and next week, Monday. After that, the entire class is over. If you guys have a specific topic you want me to cover, please feel free to reach out to me. Otherwise, December 1st onwards, all classes will be cancelled. Thank you.